So once again, I'm going to try to make sure that this is working. Testing. Testing, testing. Okay, so I'm going to get started. I changed the orientation of today's lecture from our usually scheduled content to something sort of topical because I realized that our previous work in this course had sort of ideally set us up to understand the modeling of the coronavirus spread. Branching processes with immigration are a pretty darn good simplified model for that. They're not perfect, but they do a good job capturing some of the key features. So by going through some actual numerics, moving toward the slightly more applied side of the probability theory, we can get an idea of why, of sort of potential scenarios and how much of a difference it makes acting earlier rather than later. So for those in my class who are also potentially on a chat board with me, I'm just gonna ask you to let me know if you can hear what I'm saying by responding on that chat board. Just say yes if you can hear me. So I've just asked my class members to make sure that they can hear me, and I sent a link to this video to a few other people as well. So there may be non class members watching, which is why I'm talking this way. Okay, I had one student say they couldn't hear, but now it looks like everyone can hear, so I'm going to go on with the lecture. So let me remind you, this is the goal, to use branching processes with immigration to derive a sort of formula for the growth in the expected number of cases of a given virus, so we'll have the coronavirus in mind over time, and then to see how by tweaking the parameters, which potentially means changing our own behaviors, changes those expected numbers. So let me remind you of what the setup was for a branching process with immigration. So the basic idea then is we have some population which is excuse me, reproducing over time, and at each so we're going to call the generation sizes UI. So at time 0 there is some number of individuals in the population, and then at each subsequent time, so the individuals that are already in the population reproduce, and potentially some new individuals join the population. Okay, so the idea is that in this setting, we could call reproduction community spread. That's the term that's being used in the media about the coronavirus transmission. And then what we called immigration are arrivals from elsewhere, right? People who went away to the rest of Canada or abroad over spring break, came back and brought the virus with them. Or people who went on cruises or whatever. Okay, so we're gonna have this. So the community spread is the idea is before sort of while contagious, each member of the population uh, potentially gives the virus to a random number of other people. So I'm going to keep drawing sort of the community spread as this reproduction in green, and the new individuals, the arrivals from elsewhere in red. Okay, and so there's sort of two parameters to the model, which were um, the um, the offspring. Well, it's these these two parameters. So x is the this sort of offspring distribution here. So that's the random number of people that each infected individual then in turn infects, and then y is this. We could call it an arrival distribution now. Okay, and so then the way the model works is we have some initial population of infected individuals, and then in general we could say that in generation n plus 1 you have all of the individuals, so you have the new arrivals yn, and then you have the random number of infections that each of the individuals of the previous generation caused. So those are these are independent random variables with distribution with the same distribution as x, and this has distribution y. Okay, so there's a couple of things to clarify here. One is, I mean, if individuals in a family come back, they all have the same infection, then maybe it makes sense to treat them as a single. Their infection rate is their infection rates are not independent. They maybe tend to hang out with the same groups, but somehow from a abstract modeling perspective, this is still pretty reasonable. Maybe it just means that sometimes you want to treat sort of a family as effectively acting as a single individual from the purposes of the model or something like that. Okay. The other thing to clarify is that here I'm talking about generations, but it's not really clear what that should mean, right? So what I'm thinking of as a generation is sort of that corresponds to the average transmission time of so the average time between when one person gets the virus and the time that they pass it on to another individual. So we're going to care about actual numbers today. So here's sort of a reasonable estimate for that number at the moment, is something like 4 days in a scenario. So this is, our information isn't perfect about this. People, there's sort of, I'll put up some references. These slides, I have a sort of fully written version of these slides with some links. One of the studies, non-refereed study, but nothing, it's everything's happening so fast, things haven't been refereed. One of the studies seems to suggest that by about 9 days after infection at the moment, even though people still have a detectable viral load, they're actually not transmitting versions of the virus that will survive in other people. But our information is very incomplete. We also know that in some people the virus survives for several weeks, particularly if they get a bad case. But so where's this 4 days coming from? So what I'm imagining here is, so it seems to be that 5 or 6 days is the time for infection until you start to show symptoms. So if you imagine that people are spreading the virus for days 1 through 5, and I'll leave a space. I want to add to that, and then are becoming symptomatic on average, and therefore are self-isolating on day 6. Okay, you might say that's sort of not how people are actually acting. Some people aren't self-isolating, so this is maybe an optimistic scenario. But I mean, I really don't have enough information to comment on that. Here, it does seem like the viral load is increasing over time. So that maybe suggests that you're more likely to pass the virus on toward the end of the period when you're symptomatic, but when you're infected but not symptomatic. I'm just trying to see. Okay. I just had a student say they couldn't see what was being written, but that problem seems to have been fixed. Sorry about that. Okay, so I'm imagining that that's sort of on average it's 4 days between these sort of infection events. And maybe a more precise model might have what's called an age-dependent branching processes, where these the edges of this tree have lengths corresponding to the time it took for that infection. The time between the 2 infection events. That doesn't end up changing the math very much in this particular scenario. But if you want a more precise model, you might use an age-dependent branching process. Okay, one other thing I'll mention, there's this model, there's these numbers over here, which are just the raw numbers, right? But this tree structure that describes sort of who passed the virus to whom is useful information. And what do I mean by that? Well, how do we have access to the tree structure? If we do, it turns out that viruses, at least this virus, mutates rapidly enough that we can make inferences about when sort of the most recent common ancestor of the virus in 2 different people by sequencing the viral DNA from them, right? So in Washington State, this was how, you could say inference of the tree structure was the thing that revealed community spread, or at least strongly suggested community spread. They took 2 individuals with confirmed cases of coronavirus, and they sequenced the virus and determined that the sort of divergence time of those 2 versions of the virus was recent enough that they should have had some common infection source while they were both already in Washington State. So the tree. So it isn't just the numbers that matter. The sort of genealogical structure really makes a difference to the analysis or the epidemiology of the situation. Okay, so this is our model. Let me pull this part down onto the next page, right? And what matters about this? Well, really what matters is the full distributions. I mean, the full distributions have an effect, but for a first, at a first level of analysis, we can ask about the average number of infections per individual and the average number of individuals arriving from elsewhere with the virus per generation. So I'm calling this mean R because this is the quantity that's often called, you might have seen R naught, people talking about R naught in epidemiology, the average number of cases that are the transmitted by an infected individual. And this and then this is so what's this row we said, so the average number of imported cases per generation. Okay, and what we're going to see is that so I think this is an important point to make right off the bat. Once local infection or local transmission is active, it's R that's really important. So R matters way more than rho. Okay. Obviously, before there's any local cases, rho matters. If there's no local cases, there's no transmission. But once once you're in a situation where the virus is already present and spreading through the population, that's the main thing you have to fight is R and not rho. Okay, but in early stages, I said in early stages, rho matters too. Okay, so how do we analyze, right? So this is an analysis. This is a version of analysis that we've already seen earlier in the term for my students. So we know that the expected value of UN plus 1, given that so in the next generation, 4 days later, given the current number of infected individuals, this is, well, let's just use linearity up here, right? This is, so we have the expected value of 1, and then we have the sum from 1 up to m of the expected value of x and I, right? And that's just rho plus m times the mean of x, r, okay? And so that tells us that the expected value of un plus 1 is just the sort of weighted average, so sum of rho plus mr times the probability that un is m, and that's just rho plus r times the expected value of un. Right? Just applying linearity. Okay, so we get some affine recurrence for the expected number of infected individuals over time. So if I call this mn plus 1, okay, so this expected number in generation n is mn. So then we have the following recurrence, which we want to solve, and then plug in numbers and see what we get. So we're getting mn plus 1 is rho plus r times mn. Whoops, that's not mn. Mn, right, with some initial condition so m naught is some value k, and in all of my examples, so we're starting to get to examples, I'll be taking k equals 9, just because 9 is the number of confirmed cases in Quebec at the moment. Okay, so I want to emphasize, I'm going to take k equals 9. I'll say more about that in a second, actually. So let's just say, so then what's m1? M1 is going to be, that means rho plus rk, and we want, and m2, and so on and so forth. Let's solve this. Well, if you took, say, Math 240 at McGill, you learned how to solve recurrence relations like this probably. You may have learned it even in a high school class if you had some sort of advanced math in high school. It's not really past high school level math. I just don't know if all high school curricula do this. But so let's do it. Let's write mn plus 1 then. We said it's rho plus r times mn. I'll rewrite that. And now I want to use this. I'm gonna write the same recurrence for mn plus 2. So mn plus 2 is rho plus r mn plus 1. And now I'm just going to take a difference of these two equations to get recurrence for the difference. I get mn plus 2 minus mn plus 1 is, so the rows cancel, and then I get r times mn plus 1 minus mn. Just a note for my students, in principle I can hear you if you want to talk to me and ask questions. I'm trying to remember to occasionally glance over at the text board as well, but if I forget to do that, you can try to just yell and get my attention if you're logged into the Discord server. Okay, so back to here. This is nice because now we have, rather than an affine recurrence, we have a simple multiplicative recurrence for the differences, right? So we get we have this this is a simpler recurrence. It's exponential growth, of course, and the initial condition excuse me, is what? So we said m1, that's up here, is rho plus rk minus m naught is just k. That's k r minus 1 plus rho. Okay, and so then what? We get that m2 minus m1 is just r times m1 minus m naught. So that's r times this quantity k r minus 1 plus rho, and so on and so forth. In general, we'll have, so mi plus 1 minus mi is just r to the I times this same quantity here, k r minus 1 plus rho. Okay, and now so we don't care about the differences, we care about the final value. We get mn is m naught plus the sum for I from 0 to n minus 1, mi plus 1 minus mi, just writing this as a telescoping sum. That's k plus the sum from 0 to n minus 1 of r to the I, and then this this expression here, k r minus 1 plus rho. And okay, we know how to do that geometric sum. That gives us k, the initial population, plus r to the n minus 1 over r to the n minus 1 over r minus 1, and then k r minus 1 plus rho, like that. Okay, so this is our modeling formula. This is not difficult math, but it's sort of important math. So I'm going to write it down because we're going to use this for the rest of the class, more or less. Oops, that's the wrong thing. I want this. So mn, expected number of individuals in generation n who have been infected, is this. And now let me remind you what everything here is. So I need a bit more space for that. This was the expected number of cases in generation n, which means after 4 times n number of days. Okay, assuming that the intergeneration time is about 4 days. The initial population. Okay. The R is the mean number of infections per case, and then rho is the number of imported cases per 4 days. Okay, and so I want to make two sort of important points. So one, I said that I'll take k equals 9, but that's just, I'm using that number k equals 9 because there's 9 confirmed cases in Quebec, but the truth is not about confirmed cases. It's about the number of cases. Right? It's just a convenient number to use as a proxy. Okay, and the second point is that you can see that. So let's look at this part right here. Okay, this acts as some sort of an initial condition, kr minus 1 plus rho, and then after that it's this prefactor here that contributes to the exponential growth, right? And so what that means in particular is that if k times r minus 1 is much bigger than rho, that's the point at which the imported cases don't matter anymore. Okay, and that really doesn't take so long, it seems, for that to be the case. Okay, if there are any questions about that, I think that this is sort of an important point in terms of policy, because it tells you, in terms of your estimate of the number, at any given time you should have some estimate of the current population, which acts like an initial population from then on. Right? So if your estimate of the current population, the current number of cases, tells you that that this number is much bigger than this number, then all of your efforts, or almost all of your efforts, should really be focused at that point on reducing R, on dealing with the cases on the community transmission rather than on the arrivals from elsewhere. Okay, so so let's go through a case study. So this is our case study is Quebec. Okay, and all that means by saying Quebec is this idea that k is 9. But what I'm really interested in is what happens when we vary R, the average number of cases per infected individual, and we'll also play with rho. I mean, this is sort of some sort of a scientific estimate. From what I've read, that's sort of no one knows for sure, but that's seems to be a reasonable guess for the mean value in the situation where no sort of social isolation measures have been taken or anything. Okay, and this one here, who knows? But let me start by just taking this as 1. That's maybe a lowball estimate, one person every 4 days coming in with the coronavirus. But I'll work with rho as 4 as well. We'll see that changing rho really doesn't end up being the major player in terms of what comes out of this calculation. Okay, so now let's look at right. So this is the initial population, and so let's start by looking at n is 5. What does n is 5 mean? That's 5 times 4 days. So we're talking about what things will look like roughly 3 weeks if sort of there's no action. We just all go about our business as though nothing's happening. We don't make any efforts to change our behaviors in ways that would reduce R, and there's a relatively low rate of arrivals from elsewhere. Okay, so what does our formula give us? This is the formula I'm talking about right here, right? So we're saying k is 9, and then we have 2.5 is our r to the 5 minus 1 over 2.5 minus 1, and all of that times 9 r minus 1 plus our row that we took to be 1. Okay, and if you plug that into your calculator and work out the math, it's about 953. Okay, so no action. If there are 9 transmitting cases in Quebec right now, means 950 cases in 3 weeks. And if we were all brilliant enough to continue to fail to act for another 3 weeks, so now we're looking at 10 times 4 days, so 42 days is 6 weeks, right? And now we're looking at 9 plus 2.5 to the 10 minus 1 over 2.5 minus 1 times this same quantity. Okay, and this is a disturbingly large number, about 92,197. Okay, it's kind of stressful. Right, so you know, if you think of time 0 in this estimate as being March 8th, which was the end of spring break, when lots of university students and school-age students and their parents all got back to Montreal, if you imagine that there are sort of 9 undetected cases starting then n equals 5 is March 28th, and n equals 10 is April 17th. Okay, so that's what we're looking at. I want to first go through an even more stressful estimate, which is what happens if the arrival rate from elsewhere is higher, to show you how relatively little of a difference that makes once there's local spread. So let's multiply that value by 4. Go from 1 every 4 days from elsewhere to 1 every day from elsewhere. Okay, then in 3 weeks we're talking about, so let me bring our formula back down. This is our key formula. So now we still have 2.5 to the 10 minus 1 over 2.5 minus 1, and then here 9 times 2.5 minus 1 plus 4. Okay, plug that into your calculator and you get a number which is about 1100. So that's 1100 as opposed to 953, right? That's the difference. It's an increase of 20% or something. Okay, and so then in 6 weeks you get whoops, that's supposed to be 5. That's 5 weeks. When n is 10, you're looking at that. So the only change is this, the value n there goes from 5 to 10. And then you're talking about something like 110,000. So which you're comparing to 92,000 up here. Okay, so that 20% increase might feel like a lot. Well, and it is in absolute numbers. But let's look at what happens if by some sort of action we can reduce r from 2.5 to say 1.5. Okay, so I'm going to pull this back down. That's always our key formula. So let's look now at what happens when k is 9, r is 1.5, rho is, I guess I'll start back with 1 and then I'll do 4. Okay, so now what does this situation look like in 3 weeks? Possibly 3 weeks from last Sunday or something. Who knows? I mean, we don't know what k is. But this gives us now, so everywhere there was a 2.5, we now have a 1.5. Right? And we're looking at 5 weeks. Okay. So plug that into your calculator, or if you're good at mental arithmetic, do it that way. You get a number which is about 81. Okay, so what are we comparing that 81 to? So 81 cases in Quebec in 3 weeks. We're comparing that to something around 1,000, between 950 and 1,100. Okay? And so a factor 10 difference. What about after 6 weeks? Right, so then it's the same formula, except where n has gone from 5 to 10, and you get a number which is somewhere around 632. Okay, and that number is being compared to something around 100,000. Okay, so that's rather compelling. We have 2 more examples to do. One is to see that even in the case where we reduce r still matters more than rho. Okay. So again, multiply the arrival rate by 4, and after 3 weeks, we're getting so this is the only place here that the arrival rate comes in, right? It's that 1 becomes a 4. So we have 1.5 minus 1 times 9 plus 4, and that gives us a number around 121. Okay, and when n is 10, so after 6 weeks, this calculation gives us a number around 972. Okay, so again, changing rho by a factor of 4 here is changing the picture in 3 to 6 weeks by 50% more, right? That's 120 versus 80, 900 versus 600. It's not insubstantial. You can't say that it doesn't matter, but compared with the difference between difference between 80 and 120 versus the difference between either of those numbers and 1,000, or the difference between 6 and 900 versus 100,000, sort of clear where the main battle is. It's on preventing local transmission. Okay, and what's the last calculation? So let me write that down because it's really important. So we're talking about this is a summary of what we just did. Expected number of cases in 3 weeks versus 6 weeks. Right, so here we're talking about either 950 to 1100 versus 80 to 120. Assuming our modeling assumptions are valid. So that's a factor 10 difference. Okay, and here we're looking at 90,000 to 110,000 versus 600 to 900. So factor 100 difference. Okay. So what's the last calculation I want to do is about the difference between acting now versus a week from now. So how much difference does a week make? So let's actually, just because we're allowed to do this, we're mathematicians, we'll make the math easier by asking about an 8-day delay. So that's just so that in the way the sort of idealization I've set up, I can talk about 2 generations. Right, so I'm interested in running this model now with, I want to say that for the first 2 generations, we have R is 2.5, and for subsequent generations, R is 1.5. And let's fix rho equal to 4 for both. Okay, so that's 1 arrival per day, but a week from now, rather than today, we get serious, and through social isolation and obsessive hand washing, we managed to reduce R to 1.5. Okay, so those are our. Let's grab our formula again. Where was our formula? Here. There's our formula. And now, so first, we first do the calculation when R is 2.5, rho is 4, when N is 2 for the first 8 days, so we get 9 plus, and now 2.5 squared minus 1 over 2.5 minus 1. And now here we have 9 times 2.5 minus 1. This is almost the last one of these I'm going to do, I promise. Plus 4 is 70.25. Okay, and now what? So now we're saying that in 8 days, this is, so 8 days from now, this is the new initial population. That's when we get serious, but this is the number of cases already in the population. So now we want to work with K is 70, and we're interested in what happens. So before we were looking at N is 5 and 10, so after the first 2 steps, we have another, we're going to look at N is 3 and then N is 8, right? So this is, because we're interested in, this is going to be telling us about 3 weeks from now, or 20 days from now. Okay, then now we're getting, so 70 is our initial population, that's our K up here, and then we have 1.5 to the 3 minus 1 over 1.5 minus 1 times 70, 1.5 minus 1 plus 4, and that's around 255. Okay, and so that was n is 3, when n is 8, so this is now our 6 weeks from now number, because we have to add the 8 and the 2 to get 10 generations. Then we're getting 70 plus 1.5 to the 8 minus 1 over 1.5 minus 1. And now here we have the same quantity. And this is around 2,000. Okay, so what does this mean? Well, what were we comparing this to? Up here we had, if we acted immediately, 80 to 120, and down here 600 to 900. I think the the row equals 4 numbers were really the 120 and 900. Okay, so what this is saying is that a 1 week delay doubles the number of infections. Okay, so that's I think fairly compelling case for acting sooner rather than later.